So, welcome to Trusting AI in High Integrity Systems. My name is Dominic Taylor. I'm going to start this presentation by explaining what I mean by high integrity systems before talking you through the well-established process of risk assessment and assigning levels of trust that is used for high integrity systems to ensure they behave as intended. And then finally, I'll talk about a very important part of high integrity systems where the technology interfaces with human beings and how unforeseen and undesirable things can happen. So what do we mean by high integrity systems? Well, there's certain systems in which we place a very high level of trust to behave in a certain way and which can have catastrophic consequences if they go wrong. So to illustrate this with an example from the 1988, the Clapham rail crash, in which a single stray wire in the high-integrity signalling system controlling train movements resulted in two trains being authorised at high speed into entering a section of track that was occupied by another train, causing the untimely deaths of 35 people and injury of nearly 500. So when we talk about high-integrity systems, what we actually usually mean is systems that need to perform certain functions with high integrity. So like authorizing a train to proceed down a section of track is inherently a high-integrity function. But that doesn't necessarily mean that all the functions performed by a high-integrity system need to be of high integrity. There may be certain data logging or analytic functions that really don't require much integrity at all. So it's important to clearly define which functions we want to behave with high integrity and what exactly we want those functions to do. It's also very important to define the context in which we want to trust those functions to perform with high integrity. So thinking about another industry, the automotive industry, and a typical AI application, that of the self-driving car. Do we want to trust the car to drive on motorways? What about dual carriageways? What about urban roads? What about car parks? What about rural roads? What about farmers' fields? Do we trust it to drive in the sunlight or in wet and rainy conditions as well? What about icy conditions where the grip of the wheels on the road isn't quite as good as it normally is? Do we trust it to drive on the left or on the right? Do we trust it to read speed signs in miles per hour or in kilometers an hour? Exactly which countries' road signs do we expect it to interpret correctly? So simply having a nebulous requirement like driver vehicle is unlikely to lead to satisfactory results. We need to be more explicit about what we're trusting the system to do and in which specific context we expect them to do that. Now, although AI and trustable AI is a relatively new concept, the use of software in high-integrity systems, albeit deterministic software, has been around for quite some time, over 40 years. And the dangers of overconfidence in software were learnt the hard way quite early on, as this very famous case study, the Theric 25, illustrates. From 1985 to 1987, the Theric 25 machine administrated very high levels of radiation to at least 6 people, resulting in some of them being killed and others very seriously injured. Now, the Theric 25 was a derivative of earlier machines that had a very successful track record. One of the key differences with Theric 25 is partly it was a dual-use machine. It administrated both gamma radiation and electron beam therapy. But crucially, it was an entirely software-controlled tool, whereas previous versions of the machine had electrical and mechanical interlocks. This one was a software-controlled device. And it turned out that there was a certain characteristics of the software that meant it could get into a certain state where it was administering much higher doses of radiation than the operator had intended or thought it was doing, which led to these accidents. And the risks of software not behaving as intended are still very much with us today, as the Boeing 737 MAX crashes in 2018 and 2019 show, killing 189 and 257 people respectively. In a sense, a slightly similar story. The Boeing 737 had a long and successful in-service track record. It was modified to make the 737 MAX, and part of that modification was the introduction of a new software system, the Maneuvering Characteristics Augmentation System. Pilots weren't actually briefed that this software system was there, and it turned out that in certain conditions, with the failure of one of its or some of its sensor inputs, it could end up in a state where it caused the airplane nose to be tilted downwards, resulting in these crashes with absolutely nothing the pilots could do about it. So given the high stakes with high-integrity systems and trusted or trustable systems, what can we do to make them generally trustable, trustworthy? Well, this is, although AI is a relatively new concept, this is actually not a new problem. This has been around since early automation systems, electrical, mechanical, and deterministic software. And there have been well-established processes of risk assessment and assigning trust that have grown up over the years to deal with this situation that could equally well be applied to AI-based systems. So typically these follow a fairly common pattern. We define the system that we're interested in, and we brainstorm what could possibly go wrong at the system boundary, what hazards could occur, things that have the potential to cause harm. And we think about what could be the causes of those hazards arising. These might be wiring faults or software bugs or mechanical faults or an interaction of things. And at the other end, we think about what could be the consequences of that hazard, and we assign them a risk score. The risk is the combination of the likelihood of harm and the severity of harm occurring. And this is important because it then allows us to prioritize where we focus our efforts. So there's some risks that we've got to mitigate at all costs. There's some risks entirely unacceptable. So something that has a high likelihood of a catastrophic accident is clearly unacceptable, and we wouldn't allow that to enter service or remain in service. So if we want it to go into service, we need to mitigate the risk. Mitigate meaning to reduce either the likelihood or the severity or both of harm occurring. And that typically brings us into this yellow region in the middle, which we call the tolerable region, where maybe there's an outside chance of something really bad happening, or perhaps a higher probability of something of a lower severity happening. But to reduce the risk for further would be disproportionately onerous. So we say it's sufficiently low that we can tolerate it, and we've reduced it so far as reasonably practicable. At the other end of the extreme, in green, we have risks that are very low indeed, so low likelihood of severity, which we can say are broadly acceptable. So the odd sort of cut and bruise or bump is probably something we can live with. And the typical consumer AI applications probably fall into that category. There are things running on computer office software, mobile phones, human home entertainment systems. If they have a few bugs and don't quite behave as intended, it's a bit of a nuisance, but by and large, not going to lead to life-threatening results. So they don't necessarily require processes in place to build in high integrity to make them trusted. But ultimately, there are systems that we do place a lot of trust in, the systems that control train movements or aircraft or radiation therapy machines or cars. We need to design them ideally so they don't fail at all, but if they do fail, that they fail in a safe manner. But it's not a one-size-fits-all, because there are different levels of trust, which we call in the safety engineering world safety integrity levels, particularly for software systems, but can be applied to electrical and mechanical systems and maybe AI systems as well. So depending on the level of mitigation that we want to achieve, the amount we want to reduce the probability of failing in an unsafe manner, it depends on the safety integrity level or SIL that we assign it. So at the top end, we have the SIL 4 system, so the things that are controlling the safe movements of trains or aircraft would typically fall into that category. And there's, of course, applications that have no SIL at all. But in the middle, there's sort of SIL 1, SIL 2, SIL 3, so maybe sort of other applications, maybe ticketing systems or seat reservation systems, where we really like to trust them a certain amount. but actually the consequences of them going wrong aren't quite as severe as a major accident. So we don't necessarily need to provide the same level of process and procedural rigor to developing them to the SIL4 integrity. When we do develop a high integrity function, we also need to consider the tools that go into developing it. So remember I said all these office applications and mobile phone applications don't really have much safety impact. That's not entirely true, because actually if you start using those low integrity tools in developing your high integrity function, then actually they have the potential to start introducing bugs in that high integrity function, or failing to detect bugs that could have a knock-on consequence in the thing behaving in an unsafe manner. So where we use tools, we need to assign a certain tool confidence level to ensure that it's suitable for developing our high integrity system. And one could well apply the same logic to the training material we use for AI-based systems. How much do we trust it to train our AI tool to behave in the manner that we intend? But even if our technical system is absolutely perfect and behaves entirely as we intended, problems can still happen where it interacts with human beings. And these interactions typically take place at various levels. May interact with a trained operator, like a train driver or an aircraft pilot, or maybe an untrained operator, like a car driver who knows how to drive a car but doesn't necessarily know about the automated driving system, or passengers. Can also interact with third parties, other aircraft, other road users, level crossing users. People are going to come along and maintain it, who are going to need to perform routine tasks, maybe run some diagnostics on it, maybe replace spare parts. And last but no least, if the system remains in service for any significant period of time, there are going to be engineers who are going to modify the system at various stages. And if you think back to the three accidents that I presented at the start of the presentation, it's worth bearing in mind that each one of those concerned what was previously a very safe technology that had been modified, and that modification had unwittingly introduced a fault in that system that caused it to behave in a very unsafe manner. So thinking about the people who might modify our systems in future and making sure they understand how the system works and what mitigations in place and what could be the impacts of modification is very important when building a system. But this interaction is two ways. Not only can engineers modifying the system have an adverse effect on it, though the system can actually mislead human operators into performing unsafe actions. So I'd like to illustrate with another rail crash, the 1999 rail crash, which at face value was simply a driver driving past a red signal into the path of another train, resulting in a high-speed collision that killed 31 people and injured 417. Well, that's not the whole story, because one of the contributory factors cited in the accident investigation was that this section of track leading into Paddington had a very sophisticated algorithm. It was a deterministic algorithm, but it might be branded AI these days, that could optimize the path of trains into and out of the station, making best use of the capacity on the track and allowing the trains to flow in a seamless manner. The trouble was, it had this tendency to route trains to the right and then to the left and then back to the right, which could be very disorientating for the drivers, leading to confusion as to where they were and where they were going. And it was suggested that this particular driver might have been misled into looking at the wrong signal and thinking he was authorized to proceed when in fact he wasn't. And one could well imagine a similar thing happening in a sort of AI automotive context, where you've got a system that can perhaps optimize driving a car or moving a plane or even a train through traffic that is algorithmically optimal, but very misleading to other road users or other operators that could lead them into performing unsafe actions. So to summarize then, whether it's AI or indeed any other high-integrity system, it's very important to define exactly which functions require high integrity, what they're meant to do, and crucially, what context we expect them to behave with high integrity. But the high integrity of a function, be it an AI function or a deterministic software function, is actually only part of the story. We need to consider the risk profile of our entire high integrity system, think about what could go wrong, and all the other mitigations that we might need to put in place to make sure the risk is reduced to either a tolerable or broadly acceptable level. And mitigation is not a one-size-fits-all. We can apply different levels of mitigation depending on the integrity we need. So some systems are very highly critical, like controlling trains or aircraft. Others less so, others none at all. But even the none at all ones, we also need to think about what influence they could have on a high integrity system if used in this development and assign them a confidence level. But finally, safety ultimately depends not just on the technical system itself, but how it interacts with human beings, because human beings have the potential to unwittingly introduce faults in the system or be misled by the system to causing it to behave or to make mistakes and perform unsafe actions. So I'll thank you for your attention. I've got 4 minutes for questions.